Okay, so we are moving right along. We've talked about ionic bondings, which is the transfer of electrons, and our ionic bonding, we are talking about making salts, metals and nonmetals, transferring electrons, so that everybody can follow the octet rule, which is more stable, which requires less energy, and that's what nature wants, the lowest energy possible. So now we're going to move into covalent bonding. In covalent bonding, we are sharing electrons so that each atom shares the electrons to obey the octet rule. So our objectives in this video here, talking about covalent bonding and introducing covalent bonding, is that we're going to apply the octet rule to atoms that form covalent bonds. We're going to describe the formation of single, double, and triple covalent bonds. We're going to contrast something called sigma and pi bonds, which you're going to learn about, and you're going to be able to relate the strength of a covalent bond to its bond length and bond dissociation energy, which is the energy required to break a bond. Okay, so first off, we need to think about, why do atoms bond in general? Atoms bond because they want to gain stability when they share electrons. When a covalent bonds, they want to gain stability. Covalent bonds are sharing electrons. The same way ionic bonds are gaining stability. They don't like to be ions. They like to be bonded together at a lower energy level and gain stability. So when we're talking about covalent bonds, we're talking about stability gaining, and these atoms are sharing electrons. They are at a lower energy state when they share electrons, and it makes them more stable. So gaining or losing electrons makes atoms more stable because we form ions that have noble gas electron configurations. And remember, sharing valence electrons with other atoms also results in a noble gas electron configuration. So in ionic bonding, remember we looked at the periodic table, and we could look and say that lithium loses an electron so that it can have a noble gas configuration. That does not mean lithium becomes helium. It means that lithium is still very much helium. There's still lithium is still very much lithium. There are still 3 protons in the nucleus, which makes it very much lithium. But however, now it's just more stable because it has lost the electron, ready to bond with something else to make a lower energy state. So, atoms in non-ionic compounds share electrons. Now let's remember, ionic compounds were when we had a metal. Well, see if my board works right, and a non-metal. Well, that just looks awful. Probably need to do that ink note. Alright, so in a chemical bond that results from sharing electrons, we have a covalent bond. Generally, covalent bonds are between 2 nonmetals. Our nonmetals, remember, live on the right side of that stair-step line. So when we share them, we have a covalent bond. The shared electrons are part of a complete valence shell for both bonded atoms. You count them for both atoms. And a majority of the atoms form covalent bonds. Now, a molecule is formed when 2 or more atoms bond. So you have a couple of vocabulary words, covalent bonding and molecule. Those are the ones that form when 2 or more atoms bond. Let's see if I can. Okay, so continuing with why atoms bond, there's a couple of molecules that exist diatomically. That means they exist in pairs. So when you see them in nature, you see them together with each other. They're not just by themselves. They exist this way because it is a lower energy level for them to exist this way. And nature prefers a more stable state than single electrons. The ones, you make sure that you have to memorize these. So let's make sure that we have hydrogen, fluorine, nitrogen, oxygen, chlorine, bromine, and iodine. Those are your diatomic molecules. Now, easy for you to remember, if you look at the periodic table on your screen, start with nitrogen, go across the fluorine, and go down. It makes the number 7. All of those are your diatomic molecules. The only one missing from right there is hydrogen. So make the number 7, starting with nitrogen, going to fluorine, down to iodine, and then just don't forget hydrogen. There are 8 diatomic molecules that you need to know. So when you see these written down, you always see them written as H2, F2, N2, O2. When they're by themselves, they exist in pairs. Because they are at a lower energy level, nature prefers this lower energy level. There we go. So, the most stable arrangement of atoms exists at the point of maximum net attraction. This is where the atoms bond covalently and form a molecule. So these atoms, these 2 fluorine atoms that you see in this picture on your screen, if you look at their Lewis structures, each one of them have 7 valence electrons. They really would like to have 8 to obey the octet rule. So they get closer together, closer together, closer together until they reach just the right point where they come just close enough for a maximum net attraction. Just close enough to where they attract to each other and they form a covalent bond. If you see in the picture here at the bottom, the fluorine, there's 2 red dots. Those dots are the pair of electrons that are being shared, the bonding pair of electrons. And it completes the octet. It's shared by the fluorine over here on the left and the fluorine on the right. It is a covalent bond because they are sharing them to complete the octet. So single covalent bonds, this occurs when only one pair of electrons is shared. The result is, again, a single covalent bond. Single pair of shared electrons. So the figure that we have here is of hydrogen. The figure shows 2 hydrogen atoms. They're forming a hydrogen molecule. That's where the 2 hydrogen atoms come together. They come together with a single sharing bond or a single covalent bond, and it results in an electron configuration like helium. That does not mean it is helium. So look at the picture. You have hydrogen, it's Lewis structure with 1 electron, and you have the other hydrogen, the Lewis structure with 1 electron. They come together all the way over here so that you can kind of see that it reaches a point where they reach the perfect maximum point where they are attracted to one another, and now they are sharing 1 pair of electrons, which is a single covalent bond, singly sharing electrons. So, review again what are Lewis structures. You've seen 2 for hydrogen and you've seen it for fluorine. The Lewis structure are these dots. They're lines. You can also use lines. And they're used to symbolize single covalent bonds. So if we think about Lewis structures, and let's first think about our halogens. Halogens are your group 17 elements. They begin with fluorine and they go down in a group, straight down in a column. Those have 7 valence electrons, and they form single covalent bonds with atoms of other non-metals. Atoms in group 16, which starts with oxygen and down. They can share 2 electrons and form 2 covalent bonds. Water is formed from 1 oxygen with 2 hydrogen atoms, and it's covalently bonded to it. So, here you have the oxygen. Look, it's missing. If you look at the picture on your screen, you see that it's missing 2 electrons to be a complete octet. Well, hydrogen has 1 electron. So if 2 hydrogens hooked up with the oxygen came together, then each of the 2 hydrogens can donate an electron here and an electron here, and voila, you have the Lewis structure for water. Let's talk about atoms in group 15. Atoms in group 15 begin with nitrogen and go down the column. These form 3 single covalent bonds, and the example that I'm giving you is ammonia. Ammonia forms 3 single covalent bonds with 3 different hydrogens. If you look at nitrogen's Lewis structure, you'll see that there are 3 unpaired electrons right here. There's electron here, and electron here, here, and here. Now, it needs 3 more electrons for it to have an octet, to have a stability. Look at hydrogen. It only has 1, and it sure would like to have another one. So 3 hydrogens can go here, here, and here, and bond with that nitrogen. So now nitrogen has 8 electrons around it, 2, 4, 6, 8, and hydrogen has 2, which is what hydrogen wants, 2 here, 2 here, and 2 here. Now they have formed single covalent bonds, and they are sharing them. Single covalent, sharing. Atoms of group 14 elements form 4 single covalent bonds, such as methane. Look at carbon. Look at the picture of carbon. You have the Lewis structure here. It has 4 dots around carbon, and it sure would like to have 4 more. Well, if 4 hydrogens come along, and each of the hydrogens shares with a carbon, then now we have 8 electrons around carbon. It has obeyed the octet rule, and hydrogen is happy as well because it now has 2 electrons around hydrogen. And so it is obeying its octet rule, which is really a duet rule because it only has 2. So let's stop and take a look. Let's stop and draw Lewis structures for each of these molecules. Let's make sure we understand how to do this so that we can see for ourselves the covalent bonds going on in these molecules. So phosphorus, to draw the Lewis structure, remember you look at the periodic table and you find out how many valence electrons are in phosphorus. And phosphorus has 5 valence electrons. Hydrogen has 1 valence electron, but we have 3 of them. So 3 times 1 is 3. So 5 plus 3 gives me 8 electrons. So for phosphorus, I put hydrogen never ever goes in the middle of a Lewis structure. Most all the time you put the least electronegative element in the middle, but in this case phosphorus is going to be in the middle because hydrogen can only have 2 electrons. It cannot exceed that. So it can't go in the middle and have electrons coming off of it. Hydrogen will never look like this with molecules over here or anything like that because now hydrogen has 8 electrons and that is a no-no. So phosphorus is in the center, and now we have hydrogen. So let's see, we have each one of these lines counts as 2. So I've got hydrogen, hydrogen, hydrogen. So I've got 2, 4, 6, and I put a lone pair of electrons on phosphorus. So now I have 8. So the Lewis structure for pH3 is 2, 4, 6, 8. This one, the picture that you see right there, that is the Lewis structure for pH3. Now let's do H2S. Well, hydrogen has 1 electron, but there are 2 of them, and sulfur has 6. So now we have a total of 8 electrons. So for hydrogen sulfide, we have an S in the center, and then we have H's on either side. So I have 8 electrons. I've got 2, 4, 6, 8. So now everybody's happy. Sulfur has 8 around it. Hydrogen each has 2. It's good to go. Let's do HCl. Hydrogen has 1 and chlorine has 7 valence electrons, which makes a total of 8 electrons. So we have hydrogen and chlorine. That makes 2. So now we have 3, 4, 5, 6, 7, 8. That is the Lewis structure for hydrogen chloride. Now carbon tetrachloride. Carbon has 4 valence electrons, and chlorine has 7, but there are 4 of them. So 4 times 7 is 28, plus 4 gives me 32 electrons. So I'm going to come over here and do carbon. Carbon always goes in the center. It is the least electronegative element between carbon and chlorine. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That is carbon tetrachloride. Now the last one, nitrogen has 5 valence electrons, and chlorine again has 7, but we have 3 of them. So 3 times 7 is 21, plus 5 makes 26 electrons. So nitrogen goes in the center because it's the least electronegative, and we have chlorine, chlorine, chlorine. I'm trying to write it so that it won't be, let's see if I can do better here. chlorine. Okay, so I have 26 electrons. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26. 26 electrons. Now you're probably saying, nitrogen does not have enough. Let me make sure I'm right here. 3 times 7 is 21 plus 5 is 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 26. Now I'm good. I've got a lone pair on nitrogen there. So now everybody has 8 electrons around them. We're good to go. That is how to draw the Lewis structure of these molecules.